Hello everyone. Since we have this snow day, I thought I would do just a little bit of a dot diagram review, which I probably would have done in class today. So here we go. First of all, you'd go make sure you've got your list. I posted the complete list right here. Notice that the next link on there was the answers. Now the answers include only the geometries, but I'm working under the assumption that if you can get the geometries correct, then you probably drew the dot diagram correctly. So we'll just pick one down the line here somewhere and review how to do this. Maybe we'll do number 21. Well, I've done that one a couple times in class. Let's do number 24, which is NO3. And notice there's a little minus sign on there. So you have to make it big enough that you can see it. You might want to magnify. So NO3 minus. All right, so we'll go now back over to the place where I can write. And NO3 minus, you'd put right here in your molecule spot, NO3 minus. Okay, you add up your valence electrons. I'm going to assume that you have a periodic table in front of you. If you don't have one, you know that there is a copy of the periodic table on the front page of the website. All right, so N has 5 valence electrons. Oxygen has 6 valence electrons. 6 times 3 is 18. 18 plus 5 is 23. And then this minus sign means that there's an extra one. So our total number of valence electrons is 24. So 24 valence electrons. You draw your skeleton structure with the N in the middle. Now remember when we talked about what should go in the middle, we said you can consider basically 3 things. Thing number 1 is the one that's closest to the center of the periodic table. The second thing to consider is which had more bonding sites. And the third thing to consider was which was less electronegative. So if you, in this case, N meets all of those 3 things to think about. It's less electronegative, that's the third one, because O is more, electronegativity increases as you move to the right on the periodic table. So N is not as far to the right as oxygen is. Therefore, we would expect it to be less electronegative. The second thing to consider was which had more bonding sites, and N has 5 valence electrons, so it has 3 open spots. Oxygen has 6 valence electrons, so it only has 2 open spots. So nitrogen has more open spots for things to bond to. And then, of course, nitrogen is closer to the center of the periodic table. All right, so that's why N goes in the middle. Then we put our O's around it. So we'll put our O here, put one here, put one here. Sometimes I'm going to kind of run out of the lines because it's awkward writing on this thing. All right, so we have this kind of a picture. Of the 24 valence electrons that we had to work with, we can see that we have 6 in the picture because each line represents 2 electrons. So take away 6 and that gives us 18 to distribute. So if I put 18 in, I would put 6 here, because 2, 4, 6 plus these 2 make 8 electrons. And I would put 6 here for the same reason, and put 6 here for the same reason. So now I have 18 electrons in the picture as loose dots. I didn't literally draw them in because I know I'm going to have to change something. All right, so if I have all my 18 loose dots around the oxygens, you can see that I'm going to need 2 more around the nitrogen, which I do not have available. Because remember, I had 24. 6 are in the picture in this representation. That left me 18 loose electrons to put around. If I put 6 on each oxygen, that would make 8 on all the oxygens, and that would be appropriate. But the nitrogen needs 8 as well, and I don't have enough electrons to do that. So when you're 2 electrons short, we said you add a double bond. So we'll go ahead and do that. Add a double bond right here. Or now this double bond could be in any one of these 3 positions. So we would call, do you remember what that's called? when the double bond can be in any one of the three positions, we call that resonance. Resonance. When the electrons can go, or the double bond can go here or here or here, then that's called resonance. And technically, when you're dealing with resonance, like sometimes if you ever took an AP class or took an AP test, they would say draw resonance structures, and you'd have to draw all the structures like this, all the possibilities. So that would be your three. Those would be your three resonance structures. Anyway, going back to this now. So at this point, now in this of the 24, if I put a double bond in, I now have 2, 4, 6, 8 electrons around the central atom. So 24 minus 8 gives us 16 dots to put in. So I'm going to put them in 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that gives us 8 around this oxygen, and 8 around this oxygen. Do you see them? 1, 2, 3, 4, 5, 6, and then these two make 8. Same thing over here. On this oxygen, I've got 2, 4, 5, 6, 7, 8. Now, have I used my 24? Let's double check. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So now I've used the 24 and everything is satisfied. All right, the domains on the central atom, there are 3 of them. And you can see them right here, 1, 2, 3. Remember, a domain is a shared, any kind of bond, whether it's single, double, or triple, counts as one domain, or an unshared pair counts as a domain. So in this case, I don't have any unshared pairs, but I do have 3 bonds, so 3 domains. So the electron domain geometry will be trigonal planar. You'll have to use that little sheet. I'll put that little sheet on the homework page so you can find it easily. But you have to use a little sheet that told you. And I will let you use that on the test on, what is it, Wednesday? Monday, Tuesday, yeah, Wednesday. Okay, number of bonding domains, since there aren't any unshared pairs, they're all bonding domains. Non-bonding, 0. 3D structure, you're going to have a trigonal planar configuration. So it's going to look like that, and like that. That's going to be, as looking at it from the top, it's flat. Molecular geometry then, trigonal planar, that's what we call this shape. Binding angle will be about 120. Hybridization, sp2, because there are 3 bonds. Incidentally, we talked about sigma and pi bonds. In this picture, there would be a sigma bond here, here, and here. So 3 sigmas and 1 pi. What resonance means, remember we had resonance in this molecule. Resonance means that this pi bond really moves throughout the whole molecule. So it's a 1 pi bond, but it becomes a molecular pi bond instead of just between 2 atoms. Is it polar? Well, I don't think so, because the electrons would be moving toward the oxygen. See, so they go this, whoops, we won't do that. They go this way, they'd go this way, and they'd go this way, so they're all going to cancel each other out. So no, there is no dipole moment. All right, formal charge on the center atom. Nitrogen, remember we said in formal charge, the picture should show what the atom owns. So nitrogen owns 5 electrons. In this case, the formal charge is not going to be perfect because we want it to be 0. So this picture shows nitrogen owning 4. Nitrogen really owns 5, but this only shows it owning 4. And what I mean by that is, in a bond, generally one electron comes from one atom and the other comes from the other atom, except in organic chemistry, where sometimes you see, it happens a lot in organic chemistry, where both of the electrons in the bond are provided by one of the partners. But for right now, usually a bond is one electron is donated by one partner and the other electron by the other. So in this picture, one of these 2 electrons would come from nitrogen, one of these 2 electrons would come from nitrogen, one of these 2, and one of those 2. So nitrogen would be shown to contribute 4. There aren't any unshared electrons sitting around the carbon, around the nitrogen, so I meant to say around the nitrogen. So 5 minus 4 gives you a positive 1 formal charge. It's supposed to be a 4. All right, so positive 1 will be our formal charge. And if you're wondering about that, it turns out that this oxygen here would be negative 1, and this one oxygen would be negative 1. and this oxygen would be 0. So we can just real quick, 6 valence electrons minus 1, 2, 3, 4, 5, 6 of the unshared gives you 0, but then there's still 1 of these two, so that gives you a -1 overall. And same thing for this one. This one works out nicely because it's 6 minus 1, 2, 3, 4, and then one of these and one of these, 0. Now sometimes in this situation, you would see a octet expanded to put another bond in to minimize that formal charge. But in nitrogen, since the outside energy level of nitrogen is the second energy level, and there is no D sublevel involved to become involved in bonding, the outside, you just don't expand the octet on nitrogen, so you just have to leave it as a +1. Okay, so that was a review of one of them. I thought I might do one more. Let's do SF4 down here. That's a little bit of a weird one. Okay, so SF4. All right, we'll do the valence electrons. There are 6, and 7 times 4 is 28. So we're going to have 34 valence electrons. So which is closer to the center of the periodic table, which is less electronegative and all that stuff. Sulfur goes in the middle. Okay, so if I do this, 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 and this, and put the F's on, of the 34 electrons, I now have 8 in a picture. So that gives me 26 loose dots to put in. So I start putting them in, 1, 2, 3, 4, 5, 6. Does that make 8 around this fluorine? Yep. Here, whoops. Here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And now I've got my loose dots in so that everything has 8 around it. The sulfur has 8 around it. However, I don't think I've used all my loose dots because I had 26 and I just put in 24 of them, 6 times 4. So I have 2 extra ones. If you have extra dots, they go around the center. So now the total domains on the central atom is 5, not 4. Because of this unshared pair. So that's a domain, and then all these bonds are domains. Remember, any bond, single or double or triple, counts as one domain, and an unshared pair counts as one domain. All right, so we have 5 domains. So the electron domain geometry for 5 domains is called trigonal bipyramidal, or trigonal bipyramidal. Okay, the number of bonding domains here would be how many? All right, did you say 4? And the non-bonding would be 1. The 3D structure of this thing, I'm going to go here first. It's called a seesaw. So a seesaw looks like, I'm going to try and draw part of a pyramidal. Okay, there you go. So there, oops, don't want to do that. That's supposed to be a straight line I just drew. All right. All right, so there we go. Now, how many, I've got 4 bonds in. Notice, usually I don't put this in a 3D structure. I'm just going to show you where they are. So they're right up here. The other 2 electrons, that unshared pair. So I'm talking about this pair right here, sits right up here. All right, I'm going to take them out because normally I don't put them in a 3D structure. But that makes this look like a triangle here in this center plane. Can you see that? Coming down here, coming out here. So visualize this as being flat into the screen. And this goes out to the left and this goes out to the right. So if this was sitting on the ground, you see how this guy could be pushed down and this would come up and this would go down and that would go up. It's like a seesaw or a teeter-totter, we used to call them when I was a kid. So that's why this arrangement is called a seesaw. The bond angles will be about 120, about 120 or 90. So the 90s are right here between this line and the center of that plane. It's right here. And the 120 is around from here to here. So there's none, or actually this is the 120 right here between these two. And then, or this unshared pair up here, that'd be 120 between that. between here and this pair. And it'll actually be a little bit smaller than 120 because this pair will spread out and push these together a little bit, but we don't have to worry about that. We'll just say 120 and 90. Okay, the hybridization of the central atom, since there's 5 domains, we must have gotten a D sublevel involved. So it would be S, P, 3, D, and that's on your little chart. Is it polar? Yes, because the electrons are going to push in this direction down like this, and like that, and like that, and like that. And those vectors would not cancel out. So, yes. And formal charge on the center atom, well, let's take a look at it. We'll go back over here so we can see it better. There are 6 valence electrons. There are 2 unshared. And then you subtract, so you subtract those, that makes 4. Then you subtract 1 of each of these. So the formal charge on the sulfur will be 0. It would be 6 minus 2 minus 4. And once again, when I say it shows what it owns, sulfur owns 6 electrons, 6 valence electrons. One of these, one of these, one of these, one of these is 4, and these 2 make the 6. So this picture shows what sulfur is supposed to have for valence electrons. All right, I think that's probably good enough review for right now. If you have questions on this, you could email me, and I'll post that little list on the homework page here in a moment so that you can easily find it. So good luck. Once again, if you have further questions, shoot me an email and I'll try and answer today.